How do we know when glaciers retreated, volcanoes erupted, rivers changed course, or supernovas exploded near Earth? Accelerator Mass Spectrometry, or AMS, can measure tiny concentrations of radioactive elements, or radionuclides, to provide the answers about events that happened tens to millions of years ago. Cosmic radiation and anthropogenic activities produce the radionuclides that are measured. Cosmic rays react with the Earth's atmosphere and surface, producing radionuclides like aluminium-26, which are deposited on Earth's surface by water, snow and ice, or directly produced within a rock. These radionuclides can reach groundwater or the ocean, be absorbed into river, lake or deep-sea sediments, or are stored within a rock to leave a fingerprint of past environmental conditions. So, how does accelerator mass spectrometry work? First, a sample needs to be collected by digging, hammering, and sawing rocks or collecting water. Back at the lab, samples are physically and chemically enriched, ready for AMS. Let's load the sample wheel into the AMS ion source. In the ion source, negative ions are extracted. The first magnet selects only ions with masses of interest to the researchers. In the accelerator tank, all molecules break up and negative ions are transformed into positive ions. All ions travel on to the high-energy mass spectrometer, where a second magnet divides different positive ion beams into a Faraday cup, where stable aluminium-27 is measured. The isotope of interest, aluminium-26, and the unwanted isobar, magnesium-26, produce different amounts of electrons in a gas-filled detector, creating a unique fingerprint. The concentrations of aluminium-26 tell scientists information about past events on Earth. AMS is so effective that it's like filling a cathedral with white sand and finding the single black sand grain hidden inside. A special feature has recently been developed to improve AMS. In ion laser interaction mass spectrometry, or ILIAMS, negative ions from the ion source are slowed down by collisions with a buffer gas, such as helium, giving ions time to interact with the laser or gas, and the unwanted negative ions become neutralized. Hence, the magnesium cannot reach the detector. Classical AMS and ILIAMS provide ion concentrations from samples, but what do the results tell us? In practice, scientists can use radionuclide concentrations to reconstruct the effects of glaciers in the past, shed light on the impacts of modern climate change on ice sheets, and predict how climate may alter glaciers in the future. If a rock sample is collected from beneath a glacier, or a boulder that's left behind from a melting one, it acts as a time capsule for the environmental conditions in a warmer world. This rock has been exposed to cosmic rays since the glacier retreated, so aluminium-26 is produced year by year since then. AMS can measure the radionuclide concentrations, hence telling scientists when the boulder emerged from the ice. AMS can also help us to understand ocean currents by using radionuclides as ocean tracers. Oceans store and transport heat, carbon, nutrients and fresh water around the world. In the Arctic Ocean, deep water formation drives this global circulation, while melting ice sheets decrease its salinity. By measuring radionuclide tracers, we can better understand ocean currents and how they're influenced by climate change. For example, numerous anthropogenic radionuclides have been identified in the Arctic Ocean, which originated from different sources. Technetium-99, Neptunium-237 and Uranium-236 from the Sellafield reprocessing plant, Iodine-129 from La Hague reprocessing plant, and Uranium-233 and Uranium-236 from nuclear weapons testing. As we know the characteristic radionuclide signatures of emission sources, AMS detection of these radionuclides allows for water transport pathways to be reconstructed, and the timescales over which the water mass has travelled to the sampling site can be calculated. Measuring such tiny radionuclide concentrations can tell us a lot about our planet, and AMS allows an interdisciplinary research team to answer some of the biggest questions about Earth's past.